Hello, and welcome to episode 3. This is all about compounds. We're gonna finally kind of start diving into some more complicated stuff, and I'm really excited about it. So we're just gonna, get right to it. So I'm gonna start out with a basic definition of compounds. A distinct substance composed of atoms of two or more elements. And these are in a distinct ratio. The distinct ratio part is pretty important. There's a scientist, a chemist named Joseph, I hope I say his last name right, Proust? Let me know how the right pronunciation for it. And he found out about this distinct ratio. He was experimenting with it, and he called it the law of definite proportions. And he's right. Every compound does have this distinct ratio of elements in it. Any change to it would be a change in the compound, and therefore its chemical and physical properties. So shout out to you, Joseph Proust. Alrighty, so that's our definition, and kind of get us going. So we look at compounds in the form of a formula, which lists elements in their simplest representation, or their simplest unit. So any sort of formula, C6H12O6, H2O, simplest unit, everything's down to the basic ratio. But there are a couple types of formulas you can use when working with compounds, and depending on what you're doing, it'll reflect, which kind of formulas you're using, or in the case of a chemistry classroom, which formulas you might be finding. So the first one is called an empirical formula. Empirical formula. You see this a lot with combustion reactions, limiting reactants, stoichiometry, stuff like that. And that is the simplest representation of your compound, divided by the least common denominator. Least common denominator. So pretty much it's like a ratio. So C6H12O6, that's this is glucose, and that's the actual formula for the compound. But the empirical formula, say if we were getting it from a combustion reaction and we calculated it out to be like C3H4O3, and we're like, oh, that's the skeletal empirical formula, this is our actual formula. So that's kind of how it works. You can find it experimentally. Alrighty. Our next kind of formula is called the molecular formula. And that's the exact number of elements. Ooh, that got a little crazy there. Of elements in a compound, formula, molecule. So that would be like, in regarding our last example, that would be our C6H12O6. If it was, say, if we were working with H2O, that could be our molecular formula, but we might experimentally determine that like H4O2 was burned off or something like that. I don't even know if that's a thing. But so that's kind of like how empirical and molecular formulas work together. And then there's one last one, a third one. This is our structural formula. Structural. And this exactly is exactly how the atoms are bonded in space. And not like space as in space, but as in 3D, 3 planes of space. You usually see like 2 kinds of structural formulas. It does depend on the program or the teacher you're working with. One is called the ball and stick. That one's pretty easy. You know, it has your element, and then your element would be the ball, and then your bond to another element would be a stick. So like this would be a ball and stick structure. Say this was like CH4 or something like that. Another one is space filling, is what they call it. And you see this on computer programs a lot, and that's pretty much like they draw the whole molecule as it interacts with other molecules. I can't draw it very well because it's really hard to draw. But pretty much it instead of having these sticks, and they just replace that with a bigger space filling to show kind of how the orbitals work, how the electrons work, and all that jazz. So look that up. You know, just Google it. You'll get a good idea, and then you'll realize, just like, not realize, but you'll see like how weird it is to draw it on the whiteboard. Anyway, so those are our 3 kind of formulas: empirical, molecular, and structural. Keep that in the back of your head. Excuse me. I'm going to kind of go along with molecular formulas for now, just because we work with those a lot. They're pretty common, not to say that empirical and what's the other one? Oh yeah, structural aren't just as important, but you see, I don't know. At least I see molecular formulas a lot more. And so when we're looking at molecules and stuff like that, we have to realize that some molecules aren't the same as others, so to speak. One of these things just doesn't belong here. We have our diatomics, we have polyatomics. Diatomic atom isn't spelled like that. Atomics. And pretty much this just means that instead of being stable by oneself, an element stable by itself, it either needs 2 to be stable, or perhaps multiple. In polyatomics, you see a lot more, you see more compounds in polyatomics. I mean, they're all compounds, but you see more varied ones with polyatomics. Some diatomic molecules include N2, O2, F2, I2. I think Cl2 is another one as well. There's a couple more, but pretty much, unless specified otherwise, these always are stable and occur naturally as two molecules bonded together. The oxygen in our air isn't oxygen, it's O2, so to speak. You know, along with a couple other things. Well, anyway, polyatomics, those really include like 1+1 atom type, so to speak. So it could be excuse me, not H. H would make it into an acid. You could do SO4 2-, which is sulfate. Phosphate, just 3-. Carbonate. You could do a bunch of other things too, and they all have like some sort of charge on it. So those are our polyatomics and our diatomics. Teachers will probably make you memorize the polyatomics. You probably should in the first place, just because they pop up, and doing things like Lewis dot structures or even just reaction chemistry, it's good to know what charges on what, because otherwise you might get it wrong, and that would not be fun. So I'm gonna move on. I'm gonna move on to naming compounds. Naming compounds is pretty complicated. Not pretty complicated, but there is an art to it. Naming compounds. And the thing to remember with compounds is that it's really a cation plus an anion. What are cations and anions? A cation is an ion, I always have to remember, ion with a positive charge. An anion is an ion with a negative charge. But they both qualify as ions because they both have a change in number of electrons. A lot of compounds are split up into cations and anions. And that's how we kind of identify how to name them. Excuse me. So we know that in this case, cations and anions, depending on where they are in the molecule, they'll end with "ide." If they're that's the suffix we'll use. If they are not needing, there's no there's no prefix really needed for that. That comes in with more covalent compounds. But if we're looking at like CaBr, which is technically which is ionic, our calcium is a 2+, our bromine is a 1-. I knew that. So it would be CaBr2. And we would name it calcium. We'll just keep calcium bromide. And that's it. That is all you need. Another one that works, sodium iodide, NaI, sodium iodide, sodium chloride, all that jazz. Non-predictable names include things like in transition metals. And the reason why is because there are just some changes in charges and electrons. So you kind of have to do a little bit more working with that. For example, if we had PbCl4, lead and chlorine, or lead chloride in this case, how do we find the charge on the lead ion? What's the charge on the lead ion? Now, how would we find that? Because we're just given lead and Cl4, and I don't know what the charge on lead is. Well, what do you think it is? We can find it here in our table. Can you see? Okay. I need to find lead first. There's palladium. I keep getting distracted by it. Where is lead? Oh man, it's right there. Whew, hello. 82 and 207. So lead doesn't really look like it can gain or lose electrons, so we're going to have to go at it from a molecular standpoint. So we have PbCl4. How can we find out what the charge on the lead ion is? Well, we can find it using the chlorine. We know from our periodic trends that chlorine is always gonna gain an electron to obtain that noble gas configuration. So we know that chlorine almost always has a -1 charge on it. Multiply that by 4 and we have an overall -4 charge on that chlorine in lead chloride. But going back, our compound is given to us neutrally, so it means that there are no charges overall in the molecule. So it must mean that the lead has to cancel out the -4 charge. There's only one molecule of lead, so it has to be a +4. Hopefully that makes sense. Always ask questions if it doesn't. This is important. So we could write it longhand as lead 4 chloride. You see that? Awesome. And you will just put the value of the charge on the transition metal or whatever metal in Roman numerals in parentheses after its name. Chloride has an "ide" at the end because it is an anion, so it's going to have that "ide" suffix. Lead doesn't, because that's not what is going to happen to the lead. It's just going to stay nice and happy. The only time that this part of a name, the first part is has a prefix or a suffix, is if it's a covalent compound, which I'm going to show you. So we're going to take our good old friend H2O, water. This is a covalent compound, and I'm going to name it. Covalent compounds always use numerical prefixes. So in this case, it'd be dihydrogen. The di showing that there's two of them. Monoxide. The oxygen has "ide" at the end. Okay, and mono means that there's just one. If we were to do something like, CO2, we can just do, we usually call that carbon dioxide, right? So that mono isn't there. The mono really is only added on this side of the equation. If it isn't here, or there's another prefix there, or if it isn't there, then just assume that there's one. For instance, CO, it would be carbon monoxide, which is not fun, and you should definitely have like carbon monoxide detectors in your house, carbon dioxide detectors in your house, because that stuff's not very fun to breathe in. So I'm going to give you, we're kind of gonna go backwards on this one for an example problem. If we have a compound IF7, what would the name of it be? So first we have to identify what kind of compound it is, and then what kind of system we'll use. IF are both, iodine and fluorine are both nonmetals, so I'm pretty confident to say that this is a covalent compound. So we're going to use our prefixes and suffixes. For reference, use the mono, di, tri, tetra, penta system. Sometimes they can get mixed up based on what you're doing, so it's important to know which naming system to use. So in this case, the name of this compound would be iodine, or iodine. Heptafluoride. And that's it. Iodine heptafluoride, because there's 7 of them. If we had, where is it? PCl5 minus, this would be phosphorus pentachloride. Alrighty. And that's pretty much it. It takes a lot of practice, if anything, if you're getting mixed up on this. The one I see people struggle with the most is finding the charges, unknown charges on metals like lead. Other metals like copper, iron, mercury, silver, tin, and nickel will be used in the same place. Did I say gold? Gold as well, if I didn't say that already. So just to let you know, that is a thing. and don't worry about it. You'll be able to grasp it pretty soon. So I'm going to stop there. That's our total episode for today. Hopefully the next one will be something about chemical reactions or moles or something like that. So once again, thank you very much for watching. It means a lot. And tune in next week for our next episode. Thanks guys. Have a good day.